Good morning, everyone. I will introduce Dr. Hartanto as the moderator for today. So he is an assistant teaching professor in Department of Civil Construction and Environmental Engineering at the Iowa State University in the United States. He received his undergraduate degree from Petra Christian University, master degree from Charlotte University, and doctorate degree from University of Nevada, Reno, all in civil engineering with emphasis in structural and earthquake engineering. So I think he's very competent in the field of the structural and earthquake engineering. His research interests include response of structures subjected to extreme event, experimental large testing, nonlinear dynamic analysis of structures, and behavior of concrete and engineering education. So Dr. Hartanto will be the moderator for today. You can lead us with a good discussion. I give the time to Dr. Hartanto.
All right, thank you, Dr. Anthony. So good morning, everyone. So today we'll talk mostly about unbounded post-tensioned structures. And we have a very distinguished speaker today. I have the privilege to introduce my own mentor, Dr. Sritharan. He got his bachelor's degree from the University of Peradeniya in Sri Lanka, his master's degree from the University of Auckland in New Zealand, and his PhD at the University of California in San Diego. He is now the Assistant Dean for Research in the College of Engineering, and he's also the Wilkinson Chair Professor in the College of Engineering. So his research interests include earthquake-resistant design and analysis of structures, precast, pre-stressed structural systems, soil foundation structure interaction, ultra-high performance concrete, and special topics in wind engineering and wind energy system. So Dr. Sri, the time is yours. Before you start, I think I can do a short poll here. So how many of you have watched the YouTube video that was sent by Dr. Anthony? Can you please raise your hand if you have watched the video? You don't need to feel bad if you have not done so, but we just want to get the number here. I hope Dr. Anthony will raise his hand. Oh, apparently not. Okay, so very few. Okay, all right, Dr. Sri, that's the statistics for you.
Okay, that's good. Well, thank you all. Thank you, Hart. It's a real honor to be here and share with you some of the work that we have done here at Iowa State University in partnership with a number of other universities. We have had in this particular project partnership with faculties from University of Minnesota, Villanova University, and a number of students and postdocs who worked on the project now moved on to University of Alabama and Cal State Los Angeles. So the project also interacted with researchers at INCRI in Taiwan and faculty at University of Auckland in New Zealand. So it's a fairly large project, and my goal today is to just take you back to the concept of using unbounded post-tensioning in the concrete wall systems, and then try to share with you some knowledge in terms of how we have advanced the system from where it was about 20 years to where we are today. Hopefully you can see my slide. So in this particular slide, I'm showing 3 different systems. I also want to show you that, given the distance and potential challenges, I've removed all of the videos. I will try to share some of the videos through YouTube, and hopefully we should be able to see how these systems behave based on some of the recorded tests. So in this particular case, I'm introducing 3 systems here. So the first one is what we call a single rocking wall. There are a number of people have looked at this particular system. So the wall is basically anchored to the foundation using unbounded post-tensioning. I'm assuming that given that second presenter is not going to be participating, I'm going to take a little more time to invest so that we could make sure that you understand and you come along as I make progress with my presentation. So that's a very simple system, and if you're not familiar with this system, it's like having a large concrete wall attached to the foundation using a very high strength rubber band. You push on it because you're designing the post tensioning to be pretty much elastic, and that means that as you push it and let it go, it's going to be bouncing back to its original position. The advantage with that system is that it can self-center because of the post tensioning that's holding the wall, unlike the reinforced concrete wall where you will tend to have plastic deformations or plastic hinge formation, which will lead to significant damage at the base. And oftentimes we have observed in past earthquakes, those structures need to be taken down because of the extent of damage they incurred. And you could look at some of the wall damage that occurred in the New Zealand earthquake in 2011 in Christchurch. In those cases, the buildings were taken down because the repairing of the wall was considered a bit too excessive, and plus occupying that structures after those damage is not possible. Now, what you see in the middle of the slide is what we call a jointed wall system. The jointed wall system introduced something unique in that it introduced as a energy dissipating device in the middle of the wall. So you can imagine this is a large wall panel, but the wall is split into, split in the middle. And as you can see, this wall was formed using 4 different precast panels. So we connected these walls together. So if you are familiar with the press program, this system was introduced in the press program in the late 90s, where we designed this wall to be prefabricated and connected in place here. Each of the wall panel is actually anchored to the foundation using unbounded post tensioning. So it's the same concept as single wall, but by splitting the wall, one of the advantage here is that you can place some energy dissipating devices in the middle, and that by introducing them, what you're doing is that you're also introducing energy dissipation in the wall system. So the one on the left is basically a single rocking wall. One of the disadvantage, if you like, would be that it does not appear to have enough energy dissipation. So if you look at that particular wall system, the single rocking wall, or we call it SRWs, what happens is that the possible energy dissipation is there could be some viscous damping coming in a small amount. One of the things that researchers have overlooked is that as the wall rocks back and forth, the bouncing of the wall on the foundation can potentially dissipate some energy as well. Now, it does not have any hysteretic damping. What we have done in this jointed wall is introduced energy dissipation in the form of what we call a U-shaped plate. So by deforming the U-shaped plate, we are dissipating the energy. Now we go to the third picture here on the right, where it's the same concept. What people have done is they have introduced reinforcement into the connection so that it's kind of a hybrid connection. So the connection is established using a combination of unbounded post tensioning and then mild steel reinforcement. By forcing the mild steel to experience plastic deformation, you can introduce damping as well. So the notion here is that because we are exposing these structures to seismic energy, it would be necessary for these walls to have some hysteretic damping. You go back to the research done in the 80s and 90s, early 90s, I should say. There have been documents published. I think you probably know if you're working in the area. Paul Priestley textbook talk about different amount of damping in columns and beams and walls, and they put the damping amount to be about for walls in the 20-25% range. If it's a column, I think they probably use something like 25 to 30% range. Those numbers were considered appropriate because those are designed with reinforced concrete, and those reported numbers were intended to be appropriate for seismic because those numbers came out of the experimental work. Now, we actually take a look at we looked at it freshly and said, okay, for these systems, how much damping is needed? We didn't know how much damping should be given to these systems so that they will survive, fairly large, decent earthquakes. Now, if you look at all of these systems, each one has a challenge. So let me tell you what they are. In the single rocking wall, energy dissipation is a main challenge. The jointed wall system, because we split the wall panel in the middle, what I discovered was that the efficiency or the moment resistance of that wall actually goes down significantly. The easy way to increase the moment resistance of a structural member like the wall panel is to increase the lever arm between the compression and tension. We did two negative things here. One is we split the wall, so the lever arm in each wall has gone down by half. And we put the post tensioning in the middle of the wall because the earthquake can go back and forth. So that's the obvious place. That also reduces the lever arm. So the effectiveness of the wall goes down. So that's the challenge with this particular system. If we come to the third system, the placing of the mild steel reinforcement, even though they do the job that you're supposed those reinforcement to do in terms of providing energy dissipation, what we discovered is that they can be potentially damaged in an earthquake. They can go through large strains because they have to in order to dissipate energy. But when you do that, you can plastify and potentially fracture those bars, and replacing those bars, in my opinion, is almost impossible. So given all of these challenges and given the benefits of this unbounded concept, what we introduced is what we call a PREVEC system. So the PREVEC does overcome multiple of these challenges. Even in the jointed wall system, I didn't go into the detail. There's a U connector placed in between. It's a stainless steel U plate is what they were using. When you use stainless steel U plate in this middle, what the challenge is that installation of the U plate is not easy. So with a PREVEC system, which we call it a precast wall with end columns, we introduce or we overcome most of the challenges that I described to you earlier. So let's take a look at how did we overcome those challenges. In the PREVEC system, what we do is we have a rocking wall in the middle, and we place end columns at the ends of the wall. By doing that, your lever arm of the entire wall panel is going to remain the same, or more or less the same. The end columns will also contribute to moment resistance because you're going to have compression and tension developing in these columns. And we typically would install the end columns using unbounded post tensioning as well. So they will rock along with the wall. And for the connectors, we introduce what we call a O connector. It's basically a cutout of a steel plate, and they are placed on the outside surface so that it will be easier to replace after an earthquake. So literally the precast wall with end columns or the PREVEC overcome all of the challenges that people have experienced previously. The O connector will also go through primarily a tension behavior as opposed to going into compressive displacement because of the nature of rocking, as you can see here, which is from a test. And by doing analysis, by doing the proper evaluation, we confirm that the PREVEC is going to be far superior to any of these wall systems that has been studied. So for the remainder of the presentation, I'm going to focus on two systems. One is the single rocking wall, and the second is the Prevex systems. The reason we studied single rocking wall is to understand the dynamic characteristic of single rocking wall and quantify the amount of damping that one can attribute to a rocking behavior associated with this wall. We were aware of the fact that, if I quantify the damping to be about, let's say, 5% equivalent due to rocking, that 5% will not be expected in the Prevex system. The moment you introduce hysteretic damping, the velocity of the structure is going to be changed during rocking, and therefore the amount of damping that you can experience will be different as well. But we wanted to quantify the amount of damping coming from this system, amount of damping coming from this system, compare and contrast and figure out what would be the advantage. We were aware that if you have a moderate seismic zone, maybe the single rocking wall would be cheaper and easier and would provide adequate performance. That was our mindset when we got into this particular quantification. So when we do a Prevex system, I do have videos, and I will share with you at the end of the first part of the presentation. So when you look at a Prevex system, this particular test was completed at Anchorage. Basically, what you will see is that the amount of damage to the wall will be pretty limited. All of the deformation will take place here in the O connector, you can see here. And they are the ones dissipate energy. You want more energy dissipation, you throw in more O connector. Just to give you a feel for the amount of cost for these systems, at least for this project, we purchased these O connectors for $30, $40 a piece, as opposed to $300 or $400 for the U connector. So there's a big difference in terms of cost as well when we come to O connector, because these are just cut out from so you can cut out these O connectors from a steel plate using laser cutting, if you like. That's what we did. The O connector also provide a lot of flexibility. You can increase the number of connectors, you can increase the thickness, you can change the radius. So you can design the O connector to be more suitable for your need, if you like. So with that, we got started with this fairly large projects where we wanted to address several things as part of this project objective. So the first one is the anchorage of post-tensioning steel. So as you can appreciate, when you throw in an unbonded post-tensioning with a fairly large forces, and when you anchor them at the end, you really don't want those anchor to give away. If the anchors fail, obviously you're going to lose the system. So that was our major concern. The reason I say it's a major concern for us is that we did do some testing initially on the strands and discovered that those anchorage actually have some shortcomings. So the shortcoming stems from the fact that, if you're familiar with how post-tensionings are anchored at the ends, they use the 3-yaw, like a chuck system at the end. So in these cases, we are using a multi-anchor barrels. Those chucks or the 3-yaw systems have to be designed such a way that they don't cut into the strand. So typically, if you take a 3-foot or a meter long strand, put anchorage at both ends and pull on it on a uniaxial test machine, 90% of the time you will find that the strands will fracture at the anchorage. Now, which is a concern for us because we want to be able to develop inelastic strains. So we wanted to make sure that the anchors can perform well. So what we discovered was those anchors typically available in the market may not be adequate. So we wanted to address that particular concern to make sure that that will not jeopardize our research objectives that follows this particular objective. And as I said, we wanted to be able to see the SRWs and the Prevex system in terms of the seismic performance. We wanted to understand the energy dissipation in terms of the different damping components come through. So, in other words, the viscous damping, the impact damping coming from the rocking component, and then hysteretic action if you were to include O connectors. We also wanted to understand that when you have a rocking system, and if you want to use that in a building structure, there need to be an interaction between floor and the rocking system. Will that be performing adequately? And then in all of the aspects, we also wanted to make sure that we advance the analysis capabilities of the rocking structure so that people can do the design and analysis appropriately. So this is what we went about doing this research. So we first designed a prototype building. So this was designed by a licensed engineer. What she did was she took a 6-story building and then designed that building first using cast in place concrete wall, and then replace that with a rocking wall, as you can see here. So in this particular case, she concluded that we will only need 3 rocking wall in the structure, and each of the wall will look something like that, and then quantify the amount of post tensioning. So that was our prototype structure, and this particular structure was designed for a site in Los Angeles using the site conditions and the seismic design spectrum given for that site. From that particular prototype wall, which gave us the dimension, the amount of post tensioning, the seismic mass associated with that structure, we came up with a very simple structure here, as you can see here, a full scale with mass slumped at 6 locations at the floor level, and from which we then reduce it to an equivalent system, which is a concentrated mass at one location. And from here, we then scale down to 1 to 3.6 scale ratio, so about the 3rd scale, to come up with a structural system that we can put it on the shake table. Now, with this research, once we designed the amount of post tensioning, and before we built the structure, we did look at the strand anchorage very carefully, and we discovered very quickly that whatever the strand anchorage available in the market was not sufficient to hold the strand all the way to large inelastic strains. So we worked with the manufacturer, redesigned the 3-year the anchorage system, and then tested them as individual strand as well as a multi-strand system, as you can see here. And in all cases, we ran through a series of tests and made sure that our system, the newly designed wedges, will sustain large inelastic strain. So you could see, basically, we would pull on it, and we defined 2 things. So the first one is a fracture strength. So when the first wire will break, we call it a fracture strength. And when multiple wire breaks without any loss in the strand capacity, we define the failure strength. So if you look at the right side, you could see the difference between the fracture and ultimate, and you could see that some of the lower one was the previously manufactured wedges, and you could see that we increased to a target strain limit of 2%, as you can see here with the modified strand anchorage. So that was our first step, because we know that that would impact all of our tests. Then we designed for the first part I'm going to cover is that the single rocking wall. In the single rocking wall, what we did was we designed 4 different wall systems, each with different amount of pre-stressing in the system. We varied the initial pre-stressing, we varied the seismic height, we varied the seismic shear resistance, and then we also looked at the confinement issue at the base of the wall. The reason we looked at that was, if I were to go to the base of the wall in one case here, at the base of the wall, because they're rock, you could potentially crush the cover concrete, which is not a big issue because you can always fix the cover concrete issue. But what we discovered was that that can potentially penetrate into the core concrete as well. So we wanted to see how do we overcome this particular challenge. In the past test, what we did was we used a steel channel at the base of the wall so that there won't be any crushing and spalling would take place. That solved the problem in terms of dealing with the crushing and spalling of concrete in the toe region. However, the precasters that we work with were not happy that we were using steel channels because that had cost to them, and they were questioning if it's a limited damage, they would rather go and fix it after an earthquake rather than try to put the steel channels up front. So we did make sure that that becomes one of the variables. So in some cases we include a channel, some cases we did not include the channels, and we address their concern as well. Now, what's interesting with these structural walls that are designed to be rocking, if you have done some seismic design with cast in place wall, you would have some confined region at the ends of the wall because that's where most of the concentration of the forces are going to be. But in between, the typical design will dictate minimum amount of reinforcement to control shrinkage cracks. So you could see the amount of steel that we ended up using in the walls were very limited. Now, here's another shot which shows the construction of the wall panel, and you could again see how lightly reinforced the walls are, except at the ends where we provided confinement reinforcement, and the wall panels were cast at a precast plant and then transferred to the test site. The test was done at the University of Nevada, Reno NEAS testing facility, if you're familiar with it. So basically, we put the structure on the shake table, supported by the foundation. The foundation was used so that we can anchor the post tensioning in the middle. So there's a pocket here. Hopefully you can see the mouse, and inside of which is where the post tensioning anchorage was placed. And then this wall panel, the wall foundation, was secured to the shake table rigidly so that it experienced the same excitation. The mass, remember I talked about the effective height for the shake table test and effective mass. So they were calculated. What you're seeing here is that the actual mass was placed outside the shake table, and it was transferred using a rigid link beam to the wall at the right location, so that the seismic inertia effects was transferred to the rocking wall, so that the rocking wall can experience the earthquake effects, if you like. For shake table tests, for each of the tests, we used in the order of about 15 to 18 different seismic motions. We used 2 suites of motions. The first suite of motions is what we call a spectrum compatible motion. So basically we will take a record, as you can see here, we pulled earthquake records from the past actual events. Most of these are from California, and we modified those earthquakes to match some target design spectrum. These EQ levels are considered to be that frequent event to the gray one is the design earthquake. So the first one is a frequent event. You're looking at magnitude 4, 4.5. The next one is in the 5 range, where it happens but not so frequently. The gray is what is known as the design level earthquake. So what is that we typically design for the walls to sustain. And then the yellow is basically the maximum considered earthquake. So in other words, those events are supposed to be the largest that you're expecting the wall to experience. We also took some of the recorded earthquake motions, so that those earthquake motions came from, New Zealand, Chile, US, and Japan, a number of other countries, and then we modified slightly, but they were made sure it was the actual motion with an amplification or de-amplification. The reason we did that was that, the spectrum compatible motion provides some useful information, whereas the recorded ground motion provides some other useful information. So we kind of mixed and matched. What I wanted to do is I wanted to show you some shake table tests, so you get a feel for how they perform in the actual test. But before I do that, let me just show you some damage up front, and then I'll go to the video file so you can see it. So if you look at the test observations, the EQ3 is the design level earthquake. So design level earthquake is basically an earthquake that's equivalent to a design spectrum that you have used to design the wall. And almost in all cases, as you can see here, there wasn't much damage that occurred to the wall panel. So the walls rocked on the foundations and then came back to its original position. When you look at the maximum considered earthquake, you can see there was some damage took place, and it's often confined to the cover concrete and required some superficial repair to the cover concrete. But I must say that in some cases, there was some penetration of the damage to the core concrete as well. Even though in this particular case, we did use a base channel, and in this case, the wall panel did not use a base channel. But I just wanted to give you a feel for how they appeared with and without the base channel, and the extent of damage that you would experience in maximum considered earthquake. So the maximum considered earthquake would come from a magnitude 7, magnitude 8 type event. It happens once in a lifetime of the structure is what you're expecting, but nonetheless, that's what you're expecting the structure to do. And as I mentioned, we did vary a number of things during the design. So these are different wall panels with different strength and different amount of post-tensioning. And because you don't have any energy dissipation into the system, you could say that most of this behavior was nonlinear elastic characterization is what you see here. If you look at the base of the wall and look at the compression zone to the tension zone, you almost have a linear variation between the compression and tension. And you could also see the contact length between the end of the wall to the neutral axis step, confirming the amount of contact that it had during the rocking. The figure here shows the drift versus the contact length. So the dashed line is a model that we developed and predicted, and you could see you're looking at different data points. They tend to fall along the line of what we were expecting the wall to do. What you see here is in the core regions of the wall, we were monitoring the amount of strain, because when you do experience this impact loading, the amount of strains could be significant very locally, and they dissipate quickly with height. And what we are trying to do here is to try to figure out how well we could quantify with our theoretical approach. And we concluded you could basically characterize them adequately, which means the equation that we are using for design purposes, something we developed, seem to be doing a fairly good job. When the walls are designed using unbounded post-tensioning, and when the walls are pushed beyond the expected drift level, you may potentially introduce inelastic strains in the post-tensioning. So when you introduce inelastic strain in the post-tensioning, you could experience some loss in post-tensioning as well. Intentionally, we wanted to look at what that translates to if you were to experience some intentional post-tensioning losses. Would that cause any serious concerns, down the road? So that's something we wanted to see if would that be an issue. So as you can see here in the top right figure, that there are some losses. The losses were anywhere from 5% to 10, 12%, depending on the wall that we tested. As I said, when you have a single rocking wall, the energy dissipations are primarily coming in different form. So the primary component is basically due to impact. There's inherent viscous damping that one could expect, but there's no non-structural elements or any large structural system surrounding the wall. So inherent viscous damping is going to be small. We did observe that some nonlinear hysteretic damping creeping in due to concrete experiencing nonlinearity. And as you can imagine, that happens in the toe regions of the walls, very small, and that component was also expected to be small. What we wanted to do is we wanted to see if we can quantify some of these damping so that we can estimate the amount of damping what these walls would experience. So you could see we are looking at on the x-axis, the amount of drift the wall is experiencing versus on the y-axis, the amount of damping that we quantified as a total amount of damping. So that includes, in this particular case, the hysteretic damping and the viscous damping component. And you could see that the numbers varied anywhere from 2% to 6%, depending on the wall that we used and depending on the drift level that the wall is experiencing. So as you would expect, these are very small amount of damping. It's not 25, 30% damping, but rather 2 to 6% damping is what we were quantifying based on the recorded motion. So there are a number of sensors used on the wall structure. They help us to quantify the amount of damping that these systems are experiencing. We published about a dozen papers. There's a project site I will share with you at the end. These papers are available if anybody wants to get into learning more about a specific issue. The energy loss due to impact. So if you were to look at the rocking structure, basically the structure is rocking at the base and it has a certain amount of energy, and the amount of energy is being dissipated. So every time it's rock, as you can see here, you will expect a loss. That's what's shown as the vertical step, so that at the end, you will lose all of the energy as a function of time. And that's what this figure shows. And if you look at the equivalent amount of the damping due to impact, that also vary anywhere from 0.5% to 2%. And you can see that's not a significant number. On average, we quantified that number to be a 1%. So the point I want to make here is that even though these systems were experiencing back and forth motion, and the total amount of damping that was available for these systems are very small, you're looking at in total in the 5 to 7% range, if you like, is not 20% or 25%, as you would expect for a cast in place wall to do. So the question is, how sufficient is that amount of damping? If that amount of damping is not sufficient, how much more damping do we need to provide? I mean, those are the questions we were looking for from this part of the study. So what we did was we did what we call a multiple level seismic performance evaluation to see how well these walls were performing with limited amount of damping. So for example, if I were to look at the different levels of EQs, so these are the spectrum that I'm showing for the EQ1 all the way to EQ4. And then we established, based on a number of criteria, again, I can go into the details if you have interest, at a given earthquake level, how much drift are we going to be allowing? How much acceleration we're going to be permitting? And what would be a tolerable residual drift that we would be able to take when a structural wall is subjected to these different levels of earthquake intensity motions. So in other words, if we subject the wall to EQ3, if the maximum drift is below 2%, if the maximum acceleration the wall experience is below the 1.2 G at full scale, and if the wall comes back less than 0.5% of the drift, we would claim that wall has performed satisfactorily. If it violates any of these, then we will quantify that to be unsatisfactory, at least in that particular category. The concept for this was developed using what was originally started from the SEOC Blue Book as the performance objective for different seismic hazard and acceptable performance for different levels of occupancy, if you like. So that's how we developed the criteria. I don't want to go into the details as to how did that come about. Some of these numbers were given by SEOC, so we kind of used as a guidance, and we did include some of our analyses to help us establish these performance criteria, and they were established upfront before us doing the test. So let me just recap. So I ran a series of single rocking walls. They had limited amount of damping in the order of 5 to 7%, which one would argue that's a very small amount of damping. If you go to somebody in the seismic region, a designer working in the seismic region, I think some of you probably are in that category. And if I ask you, can you actually run with a 7% damping in a structural wall, I think most of the people will say no. But what we found was that when we looked at the frequent, the occasional, the rare, or the design level, and maximum considered earthquake, anytime you see a number, it shows that we did not satisfy that particular criteria. Anytime you see this tick mark, all of these appear to be satisfactory. So just without going into the detail, you can appreciate the amount of damping that I introduced in the system was small, but for the most part, these walls were performing well. So how was that possible? Especially given that the general belief is that you need to have more damping into the system. So one of the things that we proved in this study and some of the other subsequent studies is that the amount of damping that you would need in the system is not as important or significant as people once believed. So you don't necessarily have to have 25% damping. Maybe you need 10% damping or 12% damping. But what this study tells you is that you don't need to have excessive amount of damping for the structures to survive. When you have 5 to 7% damping, obviously the maximum considered earthquake, you could see that the drifts were going higher. But if the drifts are higher, all it tells you is that it displaces more, but it satisfies the residual drift after the earthquake. So you could see 2 out of the 3 categories it performed well, but it's going to displace more. In this particular case, we did not lose the wall. They did perform and they did come back, but it did exceed the permissible limit. So one of the things, one of the messages that I want to leave with you based on this presentation is that one of the most important components for seismic design is the ability to design the wall to experience in a nonlinear fashion. So by doing the nonlinear response, as you can see here, I'm limiting the amount of force goes into the system. So that component, the fact that the wall can experience an elastic nonlinearity is more important than the amount of damping. So if I were to go back and rephrase that, in the old days, people said, don't design them to be behaving elastically, because that's not good, because they will attract more seismic force. I completely agree with that. But doesn't mean that you have to design it as a nonlinearly responding structure, plus throw in a 20-30% damping. Instead, what I would argue is that all you need is a structure has the ability to control the maximum force goes into the structure, or the maximum force that's going to be attracted, so that you can control the design. and you need to have some damping in the vicinity or in the range of 10-15%, not 20 or 30%. So that's something useful for you to keep in mind. One of the lessons that we got from going through this particular structural systems. We have developed, so given that, even though we did not expect these walls to survive the actual earthquake, and since they perform better, we actually have developed a design approach to tell people how you should actually design these walls. I mean, they could easily be designed for moderate seismic region, for example. We recommended the amount of damping that they would use for these design and establish a design procedure so that it's a cheaper way to design rocking seismic wall in structures without going into adding a lot of supplemental damping if you don't have to. So with that, what I'm going to do is I'm going to show you some videos, and then I'm going to let you think about some questions. I will stop at the end of that video so that you can ask me questions before I go to the next part of the presentation. Okay, I'm going to pull one figure. So here's a test unit. Again, I want to acknowledge that number of people participated in this project. Professor French from Minnesota, Professor Eric Musselman, he's now at Villanova University, and then precast companies, material suppliers, number of people participated, and this project was funded by National Science Foundation through that NISA program. In this particular test, you're going to be looking at a single rocking wall. So this is SRW4, subjected to 70% of attacatory earthquake motion. And I'll play this a couple of times so you can see. So I just paused this video to explain to you a little bit more. I've explained that you have the rocking wall. There's no energy dissipation except you have the post-tensioning coming in the middle, connected to the foundation. Foundation is tied to the shake table. Here's the link beam, and the seismic mast is sitting on the right side of this link beam, and the wall is going to be rocking. And you will find that the motion, so the 70% of attacatory is a fairly large intensity motion, but you will find that the wall behavior is, fairly easygoing, right, compared to what you would expect. Okay, I'll play that one more time. Okay, the next video, what I wanted to show you is the wall toe of the same structure.
How come our parents' generation could eat steak and potatoes, sugary sweets, smoke cigarettes?
Okay,
and
that's
never
not
have
part of the
chicken?
presentation. So it's the same wall, but I want you to see how aggressively it's rocking at the toe. It's honest, obviously the base of the wall experienced a lot more, but you could also look at the amount of damage the wall is experiencing at the base. It's again not significant. It's the same wall panel, same motion, except that you're looking at the wall toe. So you could see that some of the cover concrete came off in this particular motion. These were LED sensors we are actually monitoring, and we were able to quantify the rocking velocity as it approaches the wall foundation, and then it leaves. So that allow us to calculate the amount of damping if it dissipate, because it approaches with a certain velocity, bounces off with a different velocity, and we were able to quantify the amount of energy dissipation in that motion. So let me just do one more, and then I'll take up questions if you have. Okay, I'm going to take a quick break here and check with you to see what questions that you may have.
Okay, so we are ready to take some questions. So if you want to ask questions, please do not just type it in the chat box because it's hard for me to monitor, but please unmute yourself. And if you can, show your face, and you can ask your questions directly to Professor Sritharan. So if you have any question, please feel free to unmute yourself right now. Dr. Jimmy?
Okay, thank you for the presentation, Professor Sri. It was a very interesting presentation about the rocking walls. What I want to ask here is the first one for the experimental testing. You test the mesh in the wall using the rigid beam, right? What is the reason of doing that? Is there any special design on the rigid beam to the wall? Because I think it would create some stresses, right, in the wall for the connectivity to the rigid beam. And then the second one is the design method of these rocking walls. Is it the same as the normal reinforced concrete walls, or is there any special consideration, let's say for the calculation of the flexural strength, and then calculation of the shear strength on everything else? Thank you.
Well, thanks for the question, Jimmy. So the first question was about the use of the rigid link. So the reason we use the rigid link was the shake table setup is such that the UNR facility uses a mass rig outside of the table. The advantage is that you don't have to put the mass, putting the mass on top of the wall is very difficult during the testing. By putting the mass on the side, on a pin supported system, and connecting it with the rigid link allows you to simplify the test setup. And another advantage by putting the mass outside is that the rigid link can incorporate a load cell, which will measure the inertia effects going into the wall. Otherwise, you won't be able to quantify that. So those are the advantages of putting the mass outside. Otherwise, your system would be much more complex if I were to place the mass on top of the wall. The second question about the wall design. The wall design is actually very much simpler than cast in place concrete wall. All you need is that if it's an unbonded post-tension wall, you have a tension force coming from the post-tensioning, and you figure out how much tension or strain you're going to allow in the post-tensioning, and the compressive force in the wall toe is going to be equal and opposite, and from which you figure out the design resistance and move forward with that. And we have developed some guidelines to help with the design process as well.
Okay, thank you for the answer, Professor.
So for the added mass, that's mainly to satisfy the similitude requirements also, right?
Correct, yeah.
Is there any other questions? Dr. Pamuda? Can you unmute yourself?
Okay.
Oh, there you go.
Can you hear me?
Yes.
Okay, Professor Sri, I'm Pamuda from Petra Christian University. What I want to ask is, where does this nonlinear behavior comes from? Is it from concrete damage alone? Because there is no steel yielding in anywhere in the world. Is that right?
Okay, so I want to make sure I understand your question correctly. So you're saying,
The nonlinear behavior that we see from the experiment, is it coming from the concrete damage alone?
yeah, interesting question. So you're asking about, I talked about the nonlinear movement resistant, but what is yielding and what's not, how is that possible, right? That's your question?
Right.
Yeah, so the nonlinearity it actually comes from the neutral axis migrating towards. So when you start with the wall structure, your neutral axis is you compress the whole thing, so entire wall is in contact with the foundation, right? At that point, your neutral axis is, the entire wall is active. But as you push on it, that neutral axis migrate towards the compression zone and become a small region. That migration is what's actually controlling it.
Okay, thank you for the answer.
Yeah, that's a good point. Yeah. I see there's a question in the.
Yeah, I was about to mention this. So, if possible, Arif Wibowo, can you unmute yourself so you can direct your question right away, because I don't want any confusion with the question. So you're saying that for the moment frame system, is it possible that the unbounded post tension within the building system will have a self-centering behavior? So I don't know if you got the question.
Well, I think in general, if you design if you obviously had to design an unbounded post tension system to self-center, but we have used the same concept to introduce hybrid frame systems, which have been tested. Obviously I haven't covered that here. They can be designed to be self-centering. But yeah, if you want to ask the questions or if you want to elaborate on the question.
Yes, can you please unmute yourself and ask the question directly? So typing it in a chat sometimes is not the best way to ask questions. While waiting for him, is there anyone who wants to ask any questions?
Can I ask more question, Dr. Hartanto?
Yeah, please.
$20.
Okay, Prof. Sri, for the testing, this is a sheet table testing, right? For the unbounded. Why you choose this method of test? Using sheet table instead of the, let's say, quasi-static cyclic testing for the wall. Thank you.
Yeah, no, that's a good question. That's a fair question. So the reason we did that is, so one of our goal in the test, in this particular test, is to make sure that we, so if you look at what we have done in the past, I'm just looking at my, I see, okay. What we have done in the past is that most of the tests were done with quasi-static type loading. So when you do a quasi-static type loading, you lose the energy dissipation due to impact.
Oh,
And our primary focus here is to quantify that, because nobody had a clue as to what that value is. Is that a, is that a 3% or is it a 8% or so? It turns out on average like 1%. And then we also wanted to understand that the moment you manipulate the hysteretic damping into the wall, will that alter the impact damping, because the angular velocity of the wall will change. And what we found was that it will alter the characteristics, and it does alter the amount of damping. But as I said, if it's a 1-2% amount of damping is what you're losing, then so what? It's not a big deal.
okay. Thank you.
Okay, what I'm going to do is I want to just go back and talk a little bit more about the second set of tests. This is a handful of slides, and then we'll take another break. And if you have any questions from even the presentation that we had so far, you could certainly bring back and ask me the same question. I want to just share with you what happens if I were to increase the amount of damping into these wall systems. So that's my second part.
Do you want to continue right away, or do you want to take a 1 or 2 minutes break before you do that? So you can take some break too.
Okay, yeah, I'm happy to. That's fine too. So
Yeah,
we can
so
break for like.
let's take a 2 minutes break, and then so you can take some water and get your throat wet a little bit.
Okay, that sounds
and
fine.
then we'll
Yeah,
come back in 2 minutes.
Okay, sounds good.
All right. Dr. Anthony, 2 minutes break?
Yes, yes. Please, everyone can take a drink. Mine is also empty, so please refill.
Okay, is everyone back? Dr. Anthony, are you there? Okay.
Okay.
Okay, everyone is back. All right. So Dr. Sri, please go ahead.
Okay. All right, let me just share the slide again. Okay, so hopefully you can see my slide again. So in the second part, this is going to be a relatively short portion of it, and then I'm going to stop and take questions, and then I'll come back to the third part to finish it off. So in the second part, what we did was we introduced the PreVex systems and evaluated their performance as well. So here is a PreVex wall, rocking wall sitting on the foundation. The foundation is again anchored to the shake table. And you can see with the PreVex system, remember I talked about having an end column. This end column doesn't have to go all the way to the top of the wall. All you need is some anchored column that can support these energy dissipating devices, as you can see here. The O connectors, in this particular case, we had 6 of them attached to the wall panel. Again, I can manipulate the amount of damping that goes into the wall by designing the O connectors to be bigger, smaller, thicker, changing the radius, or increasing the number of connectors. So you don't have to assume that this column have to go all the way to the top. And I'll give you some example, and in some cases you will find that the columns can go all the way to the top, and some cases you can terminate it shorter if you wanted to. The columns can be made out of steel. You can use a steel tube. You can use a steel tube filled with concrete. You could use concrete columns. So I just want you to realize that there's a lot of benefits in using a PreVex system because it will add more value in terms of how your system is going to work in terms of providing the seismic resistance. Now, again, I think Jimmy asked a question earlier. You have the wall panel, the seismic mass sitting on a, they were supported on a pin jointed support, as you can see here. So if you take the wall, basically, they don't have much resistance because this is on a steel frame, which is all connected using pin connections. And then that's where the rigid link is established. And at the end of it, where we have the load cell so that the inertia force can be captured as a function of time during an earthquake motion as well. So that's what you see here. And what we did was we designed 4 PreVex systems and went through the same exercise. We modify the amount of post-tensioning. We modify the toe region in terms of minimizing damage. We modified the seismic mass. We modified the seismic resistance of each wall, and then go through a series of tests to see what would happen to these walls compared to the SRWs, which are single rocking walls. For the most part, what we observed is that they perform, the PreVex systems perform better than single rocking walls. So after design level earthquake, you could see they don't have any damage at the wall toes or anywhere. They also met most of the performance criteria that we established. I've already explained that. So in this particular case, you are comparing the PreVex are here, and these are the SRW. SRW I've already shown you, and we compared, and I already said they exceeded some of the limits, especially the lateral limit, load limit. But if you look at the PreVex systems, we passed almost all of the criteria without any problem. So I don't want to make I don't want to misinform you. The damping does play a role. Damping does help, but damping does not help or does not contribute to the extent people thought it should help in the past. So keep that in mind. So that the performance of PreVex is definitely better than the SRW, but in some cases you may find that SRW may be adequate. But if you want to improve the performance, you can certainly introduce a PreVex system. And when you introduce a PreVex system, you can dictate the amount of damping that you're going to be putting into the system by deciding on the design of the connector and the quantity of the connector that goes into the PreVex system. We compared then the PreVex system with SRW in terms of the amount of damping the different walls experience. So if I were to look at the SRW as an average, we had a total of about 6% damping on average. So impact is in the 1:1.5 ratio, hysteretic and viscous about 4%, so that's 5.7%. And you could see in the PreVex systems, we were able to introduce damping as much as 8% all the way to 15%. So you can certainly introduce more damping. The reason we introduce slightly on the higher side of damping is that there's a ACA document that permits the design of these wall system requires the amount of damping to be in the 15-18%. We wanted to make sure that these test results can be used to confirm this system for practical applications. You could see a slight reduction to the impact damping on PreVex system, and this is because when you use a hysteretic damping, it influences the amount of damping that comes from the impact because of the angular velocity changes, because the hysteretic action tends to slow the wall down during the impact, and that in turn will reduce the amount of damping. So one could see that consistently that amount of damping is about 33% reduction from year to year, 1.5 to 1. But the fact that they are 1.5 and 1, that 33 doesn't make any difference because they are small amount of damping and we can ignore it. So we concluded that we don't mind this reduction, but if one were to introduce the amount of damping here, they could quantify based on how many connectors they want to use. So if you're working in the earthquake world, you probably are familiar with the force-based design versus lately there's been a lot of work done in terms of displacement-based design. One of the things that occurred to me that in the process is that when you do a displacement-based design, you are basically allowing the amount of damping to manipulate the amount of force goes into the system. And that's why you are able to get away with the small amount of force. So the figure here shows the design shear force for the wall versus the amount of damping. So the more damping you put into the system, so that will be coming, sorry, the shear force is going to be going down as you increase the amount of damping. But if the damping is less, your force is going to go up. So that's kind of a trade-off that you have to pay attention to. And by taking an approach to the shear force as a function of damping, you can also make sure SRW also meet all of the criteria, if you like. And we have made some recommendation in terms of guiding in terms of whether you want to choose SRW or PREVEC and the amount of damping and the design force that you should use. I know there was a question earlier, and again, I can make those published papers available to you if you're interested. We have also quantified the rate of input energy. This is an interesting thing. I'll briefly touch on this. So forget the, so we were a little surprised with the way single rocking wall behaved better than we expected. Again, this is to do with the fact that single rocking wall had less amount of damping. What we discovered in the process is that if you take a look at the single rocking wall versus PREVEC, because of the angular velocity being different, or in other words, the speed at which the rolls rock, what we found was that the higher speed, when the wall rock at a higher speed, the rate of input energy doesn't go into the wall as much as it would in a PREVEC system or a cast in place wall. So in other words, the amount of energy goes into the wall also somewhat less than you would expect for other system with a lower angular velocity. And that also contribute to the wall's performance being better. This is just for us to figure out why the performance turned out to be better than people normally anticipated. And we were also struggling to understand the 5% damping alone may not be alone sufficient. And it turned out that amount of energy goes to the wall is also on the lower end or smaller than what would be the case for the PREVEC or even cast in place wall system. So that's kind of the exercise we did to figure out why the drift level was not always excessive as we expected. So let me just go back to the PREVEC system. We had, again, the same scale, 4 walls. These are the wall dimension. Unfortunately, they are in feet and inches. So that's about 2 meters in terms of the wall length. The height is about 5 meters. Wall thickness is about 125 millimeters. So because this is at 1 to 3.6 scale, you could see we used 0.6-inch strand. The amount of post tensioning was varied. The O connectors were varied, and the link beam was positioned at 2 locations to change the effective height from 14 to 11.5 feet. Again, the ground motions were very similar to what we have done before. We combined recorded earthquake motion. So you could see a number of events coming from spectrum compatible and then the real earthquake motions. These are typical sequence. So you can see in this particular case, the wall were tested for 14 different earthquakes. But in some cases, you can see we will run a white noise and then we will run an earthquake, or sometimes we repeat the ground motion, or sometimes we repeat the ground motion with a negative sign to collect additional data. So at the minimum, we recorded 14 different earthquake cycles and then continued the test for the maximum considered. And in this case, you can see we went all the way to 21 tests before we call the test to be completed. So these walls were tested very adequately. So 20 plus earthquake motion. We tested 8 walls, 4 single rocking, 4 pre-vec. One thing I would point out is that in none of the walls, we fractured the strand at the anchorage. Remember, we designed the anchorage to be different and they perform extremely well, and we did not have any problem with the anchorage failure. So with that, I'm going to stop here. Let's see if I have the video uploaded here for the pre-vec system. I don't believe. I'll pull some video, but if you have any questions, go ahead. Feel free to ask them for question. I'll see if I can pull a couple of videos to show.
Yeah. In the meanwhile, is there any questions that you have? Again, the best way is to please unmute yourself and show your handsome and beautiful faces. And you can ask the questions directly to Dr. Sritharan. Any questions?
You
Dr.
can,
Anthony, you have a question?
not yet. You can ask question in Bahasa and I will translate. Dr. Hartanto can also translate.
Yeah, feel free to ask.
Feel free, yes. Dr.
Okay,
Sritharan may also understand in some Indonesian.
Okay, so hopefully you can see my screen now. So so in the jointed wall system, this is the connector we use. So it's a bent steel plate. So this is an analysis so you could see easily. So when the wall rock, basically you're deforming the U plate. Now, because this goes through a large radius, you cannot use regular steel. We ended up using stainless steel. So that increases the cost. And when you use the stainless steel, the welding of the connector is also more difficult. Not many people can do stainless steel to regular steel welding. So those are the difficult tasks. And plus you had to take this out and put a new steel between this wall panel. And that's why we eliminated it. So with the pre-vec, let me see if I can get out of this. I don't know why it's not letting me do that. Okay, so here's a close-up of a pre-vec test that we did. This is basically showing you, so here's the wall panel. You could see, so this test was done at Anchorage. This is one of our first tests. And in this case, we use a steel steel tube. And you could see the O connectors are placed right here, all the way along the length. And so you could see when the wall rock, so this was done in a quasi-static manner. So basically the end column goes, and if you focus at the base, you could see how the wall lift up and down, and I'll show you a bit more close up as well. So you can see here in this video, you can still see, right, Hart?
Yes.
Okay, so here's a close up of the O connector. So you can see how it deforms, and you can see the extent of damage is almost nothing compared to what you would expect for a cast in place wall. So that plastic or the flexural yielding is what's basically helping you to dissipate the energy.
Okay, is there any question? There are two questions in the chat box.
Yeah, go ahead and ask.
So the first one, he was asking if you were using flat or round duct or metal or PE, PP duct. And I answered that already. I said that the selection of the duct does not really matter for this one, but it's more dictated on the thickness, by the thickness of the wall, right?
So say that question again.
What kind of duct did you use? Flat or round duct, metal or plastic duct?
So we typically use, I think we use round, but you could easily use a flat duct. I think we may have used it in one or two projects.
Right. It's more dictated by the thickness of the wall, right?
Right.
Yeah.
Yeah. If it becomes an issue, yeah, you can certainly distribute that if you like.
Yeah. And the second question, it's more on, I don't know if you remember this, but what kind of strands did you use? Is it grade 270, 0.5 inch strand or 0.6 inch strand? Is it epoxy coated?
All of them are low relaxation 0.6 inch strand.
Yeah. So that's the typical strand that we use here in the United States, 270 low relaxation 0.6 inch strand. So most of the project would use that.
Yeah, I mean, again, doesn't matter. You could use
doesn't
whatever.
Matter.
Yeah. So I think the reason we use 0.6 inch and I mean, the low relaxation is a pretty standard, and you don't want to lose pre-stressing. So that was the reason to use low relaxation. And we use 0.6 inch strand because we were trying to address the anchorage issue, and we thought that we should deal with the highest or the largest diameter available at the time. So that's the reason we ended up using that.
Yeah. And Vito, can you please unmute yourself and ask your question?
Okay, thank you for this opportunity. My name is Vito. I'm from Petra University, and I'm currently wondering about whether the additional impact on when the wall rocks should be considered when we are designing the substructure below, because as far as I'm concerned, during the rocking of the structural wall above, the mass or the forces that applies on the substructure below moves at whether the wall moves at a certain direction. So in my question here is that whether the additional impact, because when the wall rocks, usually the area of contact would be smaller, should be considered as an additional factor of the design, or should that additional impact should already be neglected because the additional impact should have been considered during the initial design of the substructure below.
So your question is that because the wall is going through an impact load, should we pay attention to the foundation design to account for the additional impact coming from the rocking wall? Is that?
I think he's trying to ask, since it's impacting the footing, would you have to design the footing to take that impact load, right? Is that your question from what I understood?
That's correct.
Yeah, it's a good question. But so typically, the amount of impact is not going to be as significant if the foundation block is large enough. So by the time the force from the top of the foundation to the bottom of the foundation, it's going to be dispersed quite a bit. And that was not an issue for us in terms of, we did quantify some of the, the acceleration on the table by recording it. And if we would be experiencing any issues, we did not really experience anything. So that's why it has not been a challenging piece. One of the things that occurred to me is that if we were to, if you have a shallow foundation, if the foundation block is sitting on the soil, in fact, it could work in your favor. The actual energy dissipation may be a little more than what you're experiencing. But we did do some evaluation, but we didn't really, we weren't able to come up with the rationale to integrate into the design, because we ran some simple tests outdoor here, and what we found was the amount of damping that soil can contribute is very dependent on how wet the soil is and how dry the soil is. So it's not just simple thing that we can deal with it. So for that reason, we decided not to incorporate that component.
Okay, thank you for the explanation.
Sure. So potentially you can design this, we did look at in one study where we could allow the entire system. So instead of the wall rocking on the foundation, can we make the foundation small and allow the foundation to rock on the soil? We did look into that, but it does go through a lot of deformation in the soil. So after the earthquake, it's harder to confirm that the condition will remain the same. Our goal is to make the structures functional after the earthquake, and we found it's difficult to make that conclusion.
Okay, Prof. Sri, maybe I want to ask the question further regarding the foundation beam, because we see that the wall itself, you use some steel channel at the bottom left and the bottom right, right? Is there any also some treatment in the foundation beam for the contact area between the wall and the foundation beam? Let's say you put some steel plates in the foundation beam.
Yeah, so so the answer is no. So I didn't really go into the details. So what we discovered was, because our precasters here wanted to avoid us using the channel, what we found was the cheaper way to do that would be to isolate the concrete cover by putting a foam inside the wall panel, so that when the wall rock, the foam squeezes but doesn't cause any damage. So that the foam is actually placed within the cover concrete to eliminate that problem. So that avoid damage to the wall as well as damage to the foundation. So in the publications, we did talk about the benefit of incorporating a piece of foam, because that's a cheaper way to do it, and it also eliminates any potential damage, because all of the forces were transferred directly to the core concrete. And if you can do that, so the reason cover get damaged and then the cover concrete comes off, it doesn't come off just cover, it also damages the core region. What was useful for us is that by isolating it, you could transfer the forces to the core, and core will not experience any damage.
Okay, thank you.
Any other questions? Any other questions? I have one question here. Maybe you can answer. So how much did it cost to do the experimental tests for all those things? So then people in Indonesia will know the cost of science here in the United States.
So this particular project, the entire project, for which we received, I believe we received $1.2 million. And then we did get quite a bit of support from a number of sources. either in kind or free labor or free material, or all of the precast walls were constructed and donated to us. So I would easily put the cost to be in the $1.8 to $2 million total. But we did quite a bit of work. As you see, we did the strand anchorage, we did 8 volt tests I kind of covered. And I want to spend a little bit more time now talking about, we keep talking about the wall, but what happens to the rest of the structure? That's what I want to spend some time now.
Okay.
That portion of the test, yeah, that portion of the test is pretty expensive. So let me get into that now. And it's an important piece, especially when you are working on self-centering systems, because if you don't address that, I don't believe the structure will self-center. So that's the reason I want to make sure that that point is adequately addressed here. So let me get into it now, and I'll share with you some interesting video at the end of this, the last portion of the presentation. Okay, so what I wanted to do now is to talk a little bit about whether it's a single rocking wall pre-vex system or any other system that when you incorporate and then you take the floors and you connect the floors rigidly to the rocking structures. I want to emphasize that it really doesn't matter whether it's a rocking structure or cast in place structure. It's the same thing. We've done the analysis to show that the rocking structure, if you look at the uplift at the first floor level, for example, and compare that to a cast in place wall, the total growth in the wall is very similar because they both go through the same lateral deformation. That's what we're designing them to. So what I'm showing here is that if I take a building floor and isolate the amount of floors that's going to be interacting with that wall, and if I allow those walls to go for a ride, I would experience two things. One is the actual resistance of that system, the composite system, the wall plus floor, is actually much higher. So you can see in this particular case, I have 40% increase. So when you do a seismic design, you design the wall for the seismic resistance or seismic design force, and then you design everything and think everything is good. But in reality, the structure is going to attract 40% more load. Some is going to go to the wall, some is going to be taken by the floor. So the floor is going to be an integral part of that you need to pay attention to. Now, the reason we specifically looked at this issue is that when the wall can self-center, if I integrate that with a rigidly connected floor system like this, as you can see here, the wall plus floor will not recenter. So the moment you connect the wall, rocking wall, or any self-centering wall to the floors and allow the system to experience inelastic action together, you will find that the damage is going to happen. Some damage will take place into the floor, and combined, you're going to get more resistance and you're going to get more permanent deformation. So a simple message here is that even if the self-centering wall can recenter, self-centering wall connected to rigid floor will not recenter. So we wanted to address this issue and figure out how do we tackle this in real building structures. So this is the point I was making. So I think you've seen the video of this wall where I showed you the close-up of the O connector. When we did the test, we actually took a reinforced concrete wall and looked at its performance. So these are equivalent in terms of their performance. This is a reinforced concrete, so you could see the extent of damage you would experience. So both walls have gone through 3% drift. This is caused by plastic hinge formation, flexural crack turning into flexure shear crack, typical damage you're experiencing. This is our pre-vex system. So there's a night and day difference between how the walls will experience. At the first floor level, if I quantify the growth or the uplift is coming from wall uplifting, you get a displacement there. So the floor has to go through that motion. Here, the wall panel doesn't uplift, but you have cracks opening up and basically gets accumulated, elongating, in essence, elevating the floor here as well. This line, blue line, is what I would expect if everything is, if it's a pre-vex system as shown here. In this case, what we find was the uplift was actually slightly higher because the cracks typically don't fully close, and therefore the growth in crack contributes to increase in uplift. So this is, again, is not a precast or rocking wall problem. It's a problem with any structures when you don't account for the flow interaction. So to address this issue, remember we designed a prototype wall, which is a 6-story prototype structure, and from which I isolated one rocking wall. So this test was done at the University of Minnesota under in collaboration with Dr. Kathy French. This is what we decided to do. We decided to build a cast-in-place floor similar to what you would experience. Obviously, you should expect 5 more floors to come in, obviously more expensive. What we did was we took the resistance coming from the 5 floors and modeled that using this rigidly connected beams, as you can see here. Because we wanted to see one floor panel, one floor, because we can observe the damage. But the rest of them, we just modeled it using this rigid or steel beam, if you like, to make sure that the simulations are going to be adequate. So that's one of the tests that we did. I'll go through the video for that test. And then the second set, we decided that we would introduce a completely different concept. Let me just go to that before I go into the details here. So the second concept that I looked at it was, you take the same pre-vex wall, but completely isolate that wall using some special connectors. So in this particular case, we rigidly connected. In the second case, what we wanted to do was we wanted to allow the wall to rock without lifting the floor. So that would completely isolate the interaction as well. So we kind of wanted to look at 2 different extremes. So let me show you a couple of videos here highlighting these tests. And these are pretty interesting tests. So okay, I'll show you a couple of videos for the first one. I'll share the screen. So this is the pre-vex system overall view. I'm looking at so you could see here's the pre-vex system, here's the floor, and you could see floor is kind of moving or deforming. You can see that, and I'll show you a more close-up view. Let me pause here. So this is a pre-vex system, but you could see that there's no columns coming all the way because I'll show you how we decided to connect the O connectors in this case in a close-up view. But in plane, basically allowing the wall panel to experience, and we also subjected this to outer plane because outer plane is a realistic load, and we looked at that as well. So this is just showing you how the test was done. And then you could also see, obviously in a building floor, you're going to have connection, so restraint coming from in the outer plane direction. So these columns were used to provide the outer plane restraints. They were not always engaged. We engaged them and disengaged them to see the effects as well. So the amount of deformation the floor panels are going through is something that you would see that they are participating in the force resistance as well. Okay, so let me just show you a close-up of that. Rigidly connected floor. Yeah, so this hopefully will show you a bit more close-up of the view. Okay, so here's the Prevex system. Here's the floor panel, and this is the outer plane restraint. You will see that sometimes we engage, we don't engage. These are all sensors. This is modeling the entire width of the building. And I want you to pay attention to the fact that how much deformation we experience here. And it's also important for you to realize that they can go through quite a large amount of deformation and maybe experience some damage that you will see during the test. So we are now at 3% drift. Now at 5% drift. So you can see the wall panel is not damaged. Okay, so let me pause here and show you. So in this particular case, we did design a Prevex system. We didn't extend the column all the way. We decided to keep the in columns to the base on the first floor only. We also decided that instead of putting the end column at the end, which maybe in this particular case could be introduce some additional restriction for us, we put it on the side. So there are more flexibility with the Prevex system. So the O connector was placed between the wall panel and this columns placed right here. Again, showing you some additional flexibility for Prevex. You can see the outer plane restraint came in here partway through the test. Yeah, some damage taking place now to the wall floor panel or floor basically. Okay, so you could see the O connectors more close up here. But the extent of damage, I mean, there is some damage taking place is very minimal compared to what you would see in a cast in place wall system. So from this particular test, what we concluded was that the flow interaction is something that you cannot avoid. You can rigidly connect the floor to the rocking wall as long as you account for the interaction that would take place and make sure that's kind of counted as part of the design, then you would be fine. So let me show you the second set of tests for the floor panel, and I'll get the video and then explain you what we did. Hopefully that comes. I don't know. Okay, I'll get the video going and then explain to you a little bit more. Okay, so in the second test, this is what we did. We had the rocking wall, and in this case, we had end column as, you can see the end column. So they are precast concrete columns is what we ended up using. The floor is basically precast floor. We decided to use a precast floor to show that you can actually use a precast floor for seismic design. So that's what got used. And the other thing that we did was we isolated using a special connector connecting the floor to the wall. So you could see, these are pre-topped, and we did not put any topping. So you can see all of the precast floors here, and they were designed to provide the load transfer as much as we used in the previous first case. Here's part of the building column, and here's the end column. So now having this end column this way or all the way to the top, there's an advantage. You can transfer the gravity load through the end columns, and that's exactly what we did. So the wall doesn't have to take the gravity load if you don't want to transfer the load accordingly. There's a connector put in, what we call a V connector, and you will see a close-up where the V connector allows the wall to uplift with respect to the floor. So in other words, the interaction was completely eliminated between the two. So with that, I'll just start the video and take a look. Okay, so you can see the V connector. So V connector has, you can see two legs, and then the stems goes inside this particular slotted hole, and anchored with this bolt going inside. So they have a super nut at the back end of it, and that's how it's done, and it's welded to the floor. And you could see how floor stays while the wall rock. So you could see the floor is not moving horizontally. I mean, staying horizontal while the wall is rocking with respect to the floor. So you could see that. So at the end of the test, we found out that this wall system never really failed. So we decided to do some bidirectional testing, and you could see how they all work together. Okay, so basically what we did, if I were to go back to the earlier slide, let me just go back to the earlier slide and make some concluding remark and then ask if you have any further questions. So if I were to go back to the first, one of the first slides that I showed you earlier, we made sure that the anchorage of the post-tensioning steel can be designed to sustain large strain. So typically a 270 KSI steel would have a strain capacity of about 0.04. We at least made sure that the anchorage can survive until 0.02. That proved to be adequate. We quantified the seismic performance of both SRWs and PREVEC, and we proved that SRW could be potentially used in seismic regions, even though they have low amount of damping. And we talked about the fact that it's more important to have the elastic nonlinear characteristics so that the amount of force goes into the system can be controlled. Damping is important, but maybe not as important as people once believed. With the 6-7% damping, system will survive. You may end up with a larger drift, but we found that the residual drift is not going to be significant. PREVEC is obviously a better solution. It gives you more freedom to incorporate damping, and you could design as much as 10 to 15, 20% damping if you wanted to. You will have the control over how much damping to put in based on how you want to design the system. But we certainly felt that both components or both systems can be used in seismic. And certainly for moderate seismic, there's no reason to do anything more than single rocking wall because it provides what you're looking for. We did spend some time to understand and quantify the interaction between the different damping components, especially the viscous damping, the hysteretic damping, and the energy dissipation due to impact. That component, we did quite a bit of work actually related to impact, and there are a number of publications came out. It turned out that the energy dissipation due to impact is not as significant as we thought, but it does play a role, especially when you design the rocking wall without any significant energy dissipation. The interaction between the rocking wall and the building floors are very important piece, and we developed two options for you. One is still you can go ahead and do a rigid floor, but expect some damage to take place to the rigid floor and expect that that damage will translate to some potential permanent deformation. So that's something you have to evaluate. Alternatively, you could use a precast or cast in place floor and isolate the interaction so that the resistance of the rocking wall only gets considered, and that way you don't have that interaction coming in. But either option should be possible as long as you account for the actual interaction in the design. As I said, I didn't go into a lot of details. Throughout the projects, we did go through analytical development so that we can come up with some design recommendation. There was a paper published which talks about how SRWs and PREVEC should be designed. We have also done publication on the design with and without incorporating flows. Again, if you are interested, some of these papers are available or at least identified on the web page. I'll see if I can. I did find out today that some of the video links are broken. I don't know what caused it, but I will get that information for you. I'll post it here, the project, and it does include most of the publication that you can you can have access to, or if you want the actual paper, I'm happy to share it as well. Let me see. Okay, I've posted the web page that has most of the information. I think if you go to the publication, you will see most of them, but I could certainly get, I'll make sure to update this one as well. So there are more than a dozen papers published on various aspects of what we have studied. And if you have any further questions, I'll be happy to answer it. With that, I'll end here, Hart.
All right, so this is the last round of questions and answers. So is there any question? Maybe I will start with a question to maybe trigger other questions.
Okay.
So if you're looking at rocking system, you can either rock at the footing, a wall to footing connection, or you can either rock at the footing to soil connection, right, or interface. So do you have any preference on which one you think is better, and why would you think like that?
Yeah, so I think, as I said, alluded to it earlier, certainly you can, there's a potential to rock the, you're talking about rocking the footing on the soil, right? If you have competent soil.
Yes, so instead of rocking wall, now it's a rocking footing.
Yeah, so we did do some evaluation on rocking the footing on soil. Couple of things that we learned. The amount of rocking that takes place, as I said earlier, is dependent on the soil conditions, not just the soil properties, whether the soil is wet or dry or somewhere in between. So having a estimate on the quantification of the actual behavior is a little more challenging. The other thing that we found was that when we did the rocking, the soil get compressed on the underneath the edges of the rocking structure. So if you start the rocking footing on a flat surface of the soil, what we found was at the end of it, the soil surface became a curved surface because it's compressing the soil on the far end. So after an earthquake, even though it was rocking, doesn't mean the structure will stay vertical because it's gone through the soil modification. So in terms of controlling the behavior, you're better off actually rocking it at the foundation rather than allow the rock foundation. That's based on the evaluation that we have done so far.
But in terms of cost, then rocking footing would be cheaper than rocking wall, right? Because we don't need to design special connections for that. Would that be a fair statement?
Yeah, I think it's fair. So it's again, so one of the things I pay attention to is that when you go into seismic design and evaluation, you won't have a handle on, if you were to have this particular size earthquake, what would I expect the structure to do? So the reason we are taking this path is to make the structures functional after the earthquakes. So with what I was saying earlier, you have a challenge to deal with. So it's cheaper, but it may not provide you what you set out to do.
Yep. All right. Thank you. Is there any other questions? Questions?
We got a lot of people online, but I guess
126 participants, including you and me. Is there any questions?
They could certainly ask questions in Indonesian, as we talked earlier. So
yes, if you want to ask questions in Indonesian, I'm pretty sure Dr. Anthony is happy to translate.
Sure.
So I need a friend here.
Yeah. Yes, Professor Sri, I have a question also.
Okay.
On your expertise in the rocking wall, what is the standing of this system compared to other seismic resistance system? So we have something twin mass damper and then the base isolation. So what do you see your system is in relation to the other seismic resistant system, and which do you think is, I mean, not how do you see the future of this system to be applied in the construction?
Yeah, so if you look at, if you look at tune mass damper or base isolation, obviously these are different technologies that people have used or are using. I think if you look at the cost of it, a rocking system like what we're looking at would be cheaper than like a base isolation type devices. But people are definitely hesitant to use this system still because they are unsure. There's some uncertainties that they have in their mind. One often come up in terms of the post-tensioning strands, breakage, and the long-term performance. While that's an issue that keeps coming up, we've been using unbonded post-tensioning in bridges for 30, 40 years. There are issues that comes up, but they deal with it. Obviously base isolation is a very different animal, and it does gives you different benefits. And in some studies recently, concerns also brought up in terms of how they would tackle vertical acceleration and things like that. So I think it's more of a preference in terms of how their designer would see. There's a designer from the Northern California has used these systems. The concept has been used in a building frames more than utilizing building like a rocking walls in structures. But what we have done is we have now codified this by incorporating this into ACI. So ACI allows what they call a special wall system, and this is considered to be a special wall system. And there's a design guide available. In fact, we are going through a revision of that document now. So we will continue to update. And one of the things that I want to update is to argue that the amount of damping that they're asking is maybe too much, and they should relax the amount of damping. And that's reflecting, so this is one of the challenges in the US, I don't know about Indonesia, is that once you do research, it takes like 8-10 years to bring it to potential use. So we are still going through that phase. But it's a preference. I would think that in the cost wise, this will not be as expensive as going through a base isolation type structures. But it's going to be slightly more expensive than cast in place structures, I would think. So if you allow precasters to come into the industry and if there's a push for precast building, certainly this would be an option to go for.
Any other questions? Any other questions? Again, if you want to ask your questions in Indonesian, you're also welcome to do so. Dr. Jimmy wants to ask a question.
Maybe my last question.
Dr. Jimmy, you asked a lot of questions tonight or this morning.
Yeah, because the topic is very interesting for me. So as the research still going on, Prof. Sri, in this post-tension unbounded ball, is there any building that already applied this system in the real structures?
So in the US, there has been very limited application so far. But in New Zealand, after the earthquake caused a lot of damage in Christchurch, they have gone through some rebuilding. So they have introduced this concept in, I don't know if they have done any concrete structures. I know they have done this concept for rocking wood building, where they've introduced this pre-wave concept.
Okay. Okay.
Yeah, I think you need to have an industry leader or champion who is excited about introducing. So if you have I presume you have some participant from precast industry attending this seminar, if they have interest and want to push this to the next level, depending on how design structures get designed and how they get approved. I mean, you know, this, you don't need to spend another $2 million to figure it out. This, all of the work has been done. I mean, you could certainly do some initial evaluation. You could design, build, instrument the building. You know, there are things that you could do to advance science instead of repeating some of these things. But a lot of the groundwork has been done in terms of utilizing the system.
Okay, thank you.
So yeah, we have some precasters here, I think. So if you want to have a discussion, you can also have a discussion. If you don't have a question, a discussion would also be okay at this point. So if you want to unmute yourself and express your opinions or concerns about this technology, you can also do so. Any questions or discussions?
So I see there is a question, or okay, there's a substructure question.
Nothing in the chat box yet.
Okay. So I didn't realize that people in Indonesia are shy to ask questions.
Oh yes. You have to offer them some gifts so then they can ask questions. So $1 from Dr. Anthony for whoever asks a question. I have to volunteer Dr. Anthony here. He's the richest man.
It's already got $10 for me.
Oh.
So
Any questions?
Anthony,
Yes.
do we have anybody from like a precast organization? Maybe,
Yeah, I think so, right?
maybe you
Dr.
could
Anthony,
ask them.
Dr. Anthony,
ask
can you
them.
introduce the precasters who are here?
Precast or precast like a
Yeah,
organization.
Yeah.
Eddie came
Eddie
online.
Susanto.
Oh,
Okay, I
there you
just
go.
sorry. My name is Eddie Susanto. I'm structural engineering. I once, because I got just entered in the webinar. Maybe I do not know detail. This is actually make a precast concrete in the cave or whatever. Is that right?
Yeah.
You make a cave in the cave, or you make a wall, or what is that? I don't know exactly detail of this one.
So hard.
Dr. Anthony, do you want to?
Maksudnya gimana, Pak?
Keep him up
Nah,
to speed.
ini apa ini? Ini bikin bangunan di bawah batu atau apa?
Oh, dia mendesain dinding tahan gempa, Pak, dari elemen
Oh,
precast.
oke.
Jadi dinding tahan gempa.
Oke.
Jadi bagaimana nanti kita bisa mendesain, dia sudah pioneer work, jadi dia lakukan dulu penelitiannya, nanti kita bisa pakai persamaannya. Kira-kira seperti itu, Pak.
Oke.
So yeah, Dr. Anthony, can you introduce the precasters here, or people from the precast industry?
Yeah.
I noticed that there's people from IAPPI also, right?
Ya, kalau ada yang boleh muncul sebentar, Bapak atau Ibu, menceritakan pengalamannya sebagai precaster ya. Jadi nanti akan saya kenalkan juga. Jadi memang di kita ini kan ada pembelajar, student and academic, terus kemudian ada peneliti gitu kan, terus kemudian juga ada yang aplikator yang membuat bangunan, yang membuat elemen, yang membangun maupun yang mendesain. Jadi macam-macam apa istilahnya spesialis kita ini ya, kita bergabung di sini untuk belajar bersama-sama tentang precast dan bagaimana kita bisa kembangkan. Mungkin Pak Henry kalau bisa dibantu juga, Pak, ada beberapa kliennya yang sudah muncul. We have ada dari.
Sebenarnya Pak ada saya perhatikan beberapa yang saya tahu dari Varia Usaha Beton Pak Agustinus Hari Laksono.
Kalau mau muncul sebentar Pak Agus boleh.
Karena harian Pak. Dia seperti manajer plan untuk Varia Usaha Beton di Gresik. Jadi memang Yang dia lakukan adalah memproduksi produk precast, UDITS, box culvert menggunakan steel table untuk fasad, sudah mensuplai begitu. Tapi tidak tahu Pak Agustinus apakah kerso ini untuk
mau boleh muncul. We have Pak Agustinus, Mr. Agustinus. He is the plant manager for the Varia Concrete. So he normally make precast element, you ditch, apalagi Pak, element wall panel and
wall panel, facade
panel also. Yeah.
But to be honest, in East Java, the reason why we try to
Promote
seminar or this webinar, it is not yet common to use precast, especially as we have informed before. There is a very strong paradigm that seismic zone is a no-no for precast. And this is exactly why we need some more information from Professor Sritharan in a simple argumentation that yes, precast is very much viable or very much valid for Indonesia, with the hope that it will boost the usage. We had been approached by several consultants in Surabaya, our hometown, and they are very eager to apply this precast to their customers. But again, it's going to be still some ways to proceed because it's about the mindset, how to convince them. That is why, Professor, if you have some information, readings, please share it with Dr. Anthony. We will surely use it also to convince that precast and the connections is a practicable in Indonesia, something like that. We have also our colleague Van Chong Thi from Rieckermann, Vietnam, where in fact some of the precast elements have been extensively used in Vietnam, like for wall, segmental wall, Architect from Elematic. It is popular there, but again, we are still not widely used, not unlike in Singapore, something like that. So that is why, sorry, Professor, the very, let's say, the very few questions because we are really in the beginning phase. But yeah, a lot of things we listen today.
So for concrete design, what design code do you use? You have Indonesian?
Indonesian, we use adopting the ACI 318. Yeah, Pak Jimmy.
So ACI has adopted, or ACI has introduced these type of systems now in the code. So you could easily bring that if you're adopting ACI. So that will be one way to bring this.
I think there's also the problem that there's no incentive of them using more advanced technology.
That could be.
From our side in the field, we always get some same questions every time. If we are talking about precast, it is too heavy. The transportation is not good enough for the infrastructure is not good enough for transporting huge element like that. Oh, we have to install a big crane. Can we do precast production beside the construction site or something like that? We still have more and more precasters who become more serious or going into something else than just you did box culvert, paving stones, but it still takes time.
Yeah, so it's not supported by the construction technology right now, I think, in Indonesia, right? So I think you have limitations.
Maybe
You have
but then,
limitations on the height of the crane that you have also.
maybe, but then also give some more inputs, because he is more, my colleague in Rieckermann Jakarta is maybe more in touch with the big boys, the precaster from the state-owned companies, and maybe he could give some inputs also.
Yeah, I think we have a lot of precaster here. Yeah, I recognize Wika Beton already. Wika Group, yeah, Wika Wijaya Karya. They already I mean develop a lot of precast building from fully precast until part of the components. I recognize here also the group from Indopora. Gema Bahana Utama also present here. I don't know. I try to chat them to give some comments. Maybe they don't have something to discuss yet at the moment, because I understand this technology, especially this wall rocking system, is still very new. Yeah, even with the I mean the old system of precast building is still not yet applied widely in Indonesia, so maybe this is still far away from our thought at the moment. Yeah, that's what I understand, because for example, the easiest maybe what is already applied in Indonesia for precast structure is still beam and column. Yeah, that's what Wika Beton is developing. They've been using Olocore, Gema Bahana. I understand. I know they use already beam and column as well. And also some pre-slab, yeah, half slab. So I think rocking system, from my view in Indonesia, maybe need more time to digest, if I could say, because this is the brand new system, and maybe need time for us to understand and to learn. Yeah, that's what I understand. But I think some of the company already here, and they hear what we discuss. I think this could be an option for them in the future, because I've seen also, yeah, if this wall rocking system in terms of the precast, it will be more simple, yeah, because we don't need to have a lot of type of wall at the later on, if we can use this as a structural. But yeah, as I said, this is new, so even with the old system that already exists for a long time, still need time to make it happen in Indonesia.
This is somehow a big homework for academic work, from our side also, the precast world, also from the government, because unlike other countries, the government give a set of clear standard and norms about precast and connections. I don't know about Indonesia. So this is why it is still not as good as like in Singapore, in Malaysia, in Europe, even in the Philippines. It is more widely
accepted.
Yeah, I mean, if precast industry, so I'm just reflecting back at in terms of how we did that. Precasters came together, and they kind of approached the academics, and then we kind of worked together to figure out what would be the appropriate system, and then we were able to find a solution that's even better than cast in place. That has helped us to help the industry to move forward because you have a better solution now.
Right.
So certainly you could come up with a similar system, do some evaluation locally at the university, and then that gives you confidence, and then you can go from there. But I think I want to emphasize that there a lot of work has been done here and a number of other places. So you're not really starting from the beginning, and you can decide to choose what is it you want to take advantage of, and what is it you want to evaluate so that it gives some confidence. There are design materials, there are ACI adaptation, so those things should help. But yeah, I think as an industry as a whole, you had to come together, and if you think this is the direction you want to go, certainly I would encourage you to push in that direction.
Yes, thank you very much for the advice, Professor.
Is there anyone else? I saw that Saiful, you have a question.
Hello, hi. Afternoon here. I'm Saiful from Malaysia. Actually, I'm the designer, one of the designer precast system in Malaysia. We have done a few projects using wall panels. It's just in Malaysia, we are quite familiar with the connection using the corrugated and grouting system. So I think I did join a bit late, I think around 15 minutes. So I couldn't see the details within the joints. Is it using post-tension strand? It's just my question is just comparing if you're familiar with using corrugated, using sleeve. In terms of installation processes, is it much simpler comparing to the grouting, or is it much complicated, or how is it the installation processes practically? Thank you.
Yeah, so the corrugated use of the corrugated pipes and anchoring bars is basically what we call an emulative kind of behavior for the wall. So you're trying to make the wall to behave like a cast-in-place wall. So if it's a seismic region or seismic load is applied to those walls, the behavior is going to be the same, and the walls will experience significant damage due to plastic information. What we have done with the Prevex system or single rocking wall is basically a different system. I wouldn't say it's a more difficult to build, but it gives you a better performance. It combines unbonded post-engineering instead of typical mild steel. So in terms of the construction, I would argue that's even simpler than using corrugated rebar system.
Okay, in term of the details work, actually we can see the detail much clearer. Is it on your website or?
Yeah, there are. I have just posted the website here. You can take a look at it.
Okay.
I think Anthony is also recording the lecture, so you can also have access to the recorded lecture.
Okay, if anything, then I can contact you later, Doctor.
Yeah.
To discuss more, maybe. Okay, thank you.
Okay.
Anyone else? Any other questions? Any other questions? Again, you can also ask in Indonesian, and Dr. Sritharan here claims that he can speak Tamil. So if you can speak Tamil, you can also ask in Tamil.
I want to just pass information from one of our customer here, Precaster. So he said that I need to revise my statement because I said that they only use a beam column, but they said for Indopora, Gema Bahana, they use precast wall, half slab and beam and stair for the precast. So, but not the whole structural by precast. And he has I think this comment, he make a comment. So I think this comment is common in Indonesia, we heard so he said, I just read it. Precast is quite new in Indonesia. Every company has their own experience, and it seems the experience still become a secret and precious experience. So it looks like it is there is a hesitation to share about their experience, because we understand that I understood from one of the from the chief of the ERP he said that I think in one of our webinar, in the first webinar, he said that because the standard, the type of the precast joint already registered by many companies before we have the code, before SNI made the code. So that's also a problem because I mean many joints already registered before there is a standard that Indonesian government made. So it's already belong to somebody. So it is not easy to use. Yeah. So that's also one of the problem that we have to solve. But I think
are you saying that those were patented? Those were patented?
Yeah.
Okay,
that was already patented before the code was made. But I heard that now it become easier because since 2019 they already make like they make it clear in the code in the law in the SNI code, and I think any precaster, any company that want to follow already have options. Not like before they have to use one of the one that it's already patented, or even make another system, new system. So that's to add to my comment before.
So in my experience in the US, when people file patent on the precast side, is not many of the connections really move forward. Even though they own it, nobody pretty much uses it. The systems that like what we are talking about is nobody's patented, and we're pushing people to use because it has more value in people using it. So something that people have to go through and look at the real experience and see, if people are protecting it, they need to make money out of this, right? If nobody is using it. So in the US, typically not many civil engineering related product, especially in the structural world in terms of connection and things like that, people made money. It just protection didn't really help. There are two things happen. Either they develop something and protect it, but somebody else come up with a slightly different modification, and that cannot be defended. So it doesn't help. Or people are keeping it and nobody wants to use it. And it has happened time and again. So not many times people actually take that path. And hopefully people in the industry can realize that there is more you can gain by sharing or selling product rather than just protecting it. In some other industry, it's a different thing, right? If you go to medical industry, it's a different world. But this is what our experience here in the US. Like if I protect the PREVEX system, we develop the PREVEX system, people won't use it. Simple as that.
Yes. Other questions or comments? I have one comment here. So if you are interested to know more about this, Iowa State University has a very good graduate program. So we invite you, good and very qualified students to apply to our graduate program. And then you can learn more about this. And we encourage you to contact me or Dr. Sritharan if you are interested in any opportunities to do graduate study here at Iowa State University. Okay, so any last question? If not, then I will count going once, going twice. Okay, so that is it. So thank you for attending this webinar, and I'll return this back to Dr. Anthony to close the webinar. Thank you.
Okay, yes, thank you, Dr. Hartanto and Professor Sri. Our discussion today is very enlightening for us. So I think this is our way of making starting point for the precast to be more accepted in Indonesia. One thing that I've considered during our webinar is like the entry point to start a precast system in Indonesia, I think is very hard, right? Because we still need to have the system, we still need to have the design, and after that we will need the equipment, and that is like the barrier to entry. Well, for the normal construction, we don't need to have any big investment in the beginning. So I think that is also one of the reason. But we already have several state-owned company who already making a very head start. They already have the precast factory, so several places in Indonesia. I think that should be a good way to start also. So thank you again, everyone, for joining our webinar on precast. So this is the 5th webinar series. The next one, the 6th, will be in 6th of November. The time we will start at 1. So I will send email to everyone for the reminder. And once again, thank you everyone for the very nice discussion, and have a nice weekend, everyone. Thank you.
Is there any, okay, already, sorry.
Yeah.
I'm asking about the evaluation question, yeah.
Oh, yes. Please fill out the questionnaires in the link, and then we can leave after this. This is for the participant. Thank you, everyone. See you again.
Thank you.
Thank you, Prof. Sri.
Thank you very much.
Bye, everybody.
Yeah.
Bye.
Hopefully, I'll be able to help you build something in Indonesia.
Yes. Thank you very much.
All right. Bye.
You're welcome to go to Petra Christian University. I think Jimmy will host you.
Sure. After this, we'll invite everyone. Okay. It's
Bye.
Thank you.
Thank you, Pak Hartanto. Thank you, everybody.
Ya, terima kasih semuanya.